So we went over what matter was last time. So we talked about mixtures and pure substances. And we talked about each pure substance divides into elements and compounds, and mixtures divide into homogeneous and heterogeneous mixtures. And we didn't complete the substance side, pure substance side, because I'd rather have a periodic table for that. And then, but we did complete the mixture side. So then we went on to say that homogeneous mixtures can be solutions, and heterogeneous are colloids or suspensions. And we kind of used one word to describe each, like when we looked at the graphic organizer, we kind of used one word just to separate them. And each person had their own word, of course, but in the mixture side, if you look at homogeneous and heterogeneous, you can say that homogeneous means, there we go, means that they're the same throughout, right? So they look the same and they are evenly dispersed, and a colloid is not necessarily, but the difference between a solution and a colloid, even though they both look like they're homogeneous, one of them will not let light go through it, which is known as the Tyndall effect, and that would be the colloid. So mixtures that are heterogeneous usually do not allow light through as a norm. So that's what you want to look at, is the Tyndall effect. So the Tyndall effect is what distinguishes solutions, and I'm talking about liquid solutions, and also gas solutions, but not solid solutions, obviously, from each other. Okay, and then mixtures, colloids and suspensions, you're using the fact that colloids don't settle out, but suspensions do. So if you have to shake it, if you think about it in your head, if you have to shake it before you use it or shake it to do anything, it's without a doubt a suspension of some sort. Okay. So that is where we were. So now we can answer this thing here. But let's see. All right. So we need to highlight or underline or something which one of these is the right one. I'm not going to be able to, because this is a PDF, and I think all I can do is annotate. So I'm going to use my annotation, but it's going to move. So I'm going to do one page at a time. Okay, so when you're looking at mixtures, we talked about them being not a chemical combination or of substances because they are physically combined. And in a compound, oh, there we go, one more. And in a compound, the atoms and molecules are chemically or physically combined. Okay, so compound, the word compound tells me that this is a pure substance. So that means that the atoms right here, right, are chemically combined to make up compounds, which means that they lose their identity and do take on new properties. Okay. And then here, let me just put a text box in. Okay, so in the smallest identifiable unit of a compound is a molecule of sorts, right? Which is made up of atoms. Okay. See? All right, is this true or false? A mixture is always made up of a combination of elements. That is false, because you can also have a combination of compounds, right? So you say false. And it says in a mixture, the substances lose or retain their identities. They actually retain them because they're not chemically combined. And in the substances can or cannot be separated by simple physical property. And like I said, when you have physical combination, like a mixture, you always have a physical separation. Now, in a compound, the elements involved cannot be separated by simple physical property, right? Because they are chemically bonded. And that's where that goes. The next one is a true and false question. It says an element can be broken down into simpler substance. Well, an element is as simple as it gets, right? So no, that's a false statement. The smallest identifiable unit of an element is, that would be an atom, right? Because an element is an atom anyway. It's simple. It's not combined with anything. So it can't be a compound, a molecule, I mean. All right, so that's where we stop with that one. So you guys got those answers already, then where I'm gonna have to erase them so that we can go on, because the screen moves. Okay. Excuse me. All right here. Okay, so we are going to select. We're going to skip, by the way, we're going to skip 10, 11, and 12 and come back to them because this is the last thing I cover. So we're just going to come back to it later. All right, but from here, we're going to circle the ones that are elements. And remember, elements are in the periodic table because that's where it's called, the periodic table of the elements. So in this case, that would be silver, oxygen, hydrogen, right? Gold, sulfur, carbon, magnesium, and I can't circle because it's harder to do that. Chromium, nitrogen, and nickel. And that's all of them right there. Okay. So if you look for them, they're all in the periodic table. They have their, each of these has their own properties. Each of these has their own number of protons, neutrons, electrons, all of that stuff. So they are separate from each other. They're different from each other. They have different properties. And we'll look at all of that later too, but just so that you learn to recognize them, they're going to be in the periodic table. They also each have their own, what would I call it, elemental symbol. So in this case, that would be silver, right? Oxygen would be oxygen like that. Then we got hydrogen. We got gold. We got sulfur. We got carbon. Magnesium. We got chromium. We got nitrogen. And we got nickel. And that's those are all the elements that we talked about. They're all in the periodic table, every one of these. All right. So like I said, we're gonna move on to the next page. So I gotta clear all of these. Make sure you get them all. If you have your printout, but I'll be giving you this printout tomorrow. So I'm gonna clear all of that and keep going on the bottom because we gotta keep moving. All right, now, see, this is a little bit more involved. Here we have to classify them as pure substance or mixture. So I'm gonna stamp all of the pure substances with a little check. So a pure substance is not a mixture. Remember, a pure substance is nothing but what it says. So water would be one, right? Mercury would be one. Sugar is a compound, so it would be one. Oxygen is an element. Alcohol, grain alcohol is actually not pure alcohol, so we're not going to stamp it. Gold would be one, and that's it. Now, the mixtures, I'm going to stamp, not that it matters, but I'm going to put a star by them just so that you know that these are mixtures. Right, there's the left ones, because air is a mixture of gases. Gasoline, we talked about how it varies in the one compound that matters, which is octane. Grain alcohol is not a pure. If you look it up, I think it's like 95% pure. And salt water, well, obviously it's salt and water, so that's a mixture too. Okay, here we're going to do hetero and homogeneous. So we're going to go ahead and stamp again. I'm going to stamp the homo first, and I'm going to do a check. All right, so in this case, oh, I forgot. All right, so if you think about it and you see it in your mind's eye, and all you see is salt water, for example, pure water, for example, and you cannot tell the difference between something and something else, then in your head, it should be homo, excuse me. And the heterogeneous, like I said, I'm going to stamp, and I forgot to put that there. So I'm going to do them with that. Okay, so sand and salt, you can see both. Yeah, you cannot see the salt. You can see the sand and the salt. You notice this is not sand and salt water. It's just sand and salt mixed together. So you definitely can see both of those. Tossed salad, obviously, you can see all those components. Unfiltered air. The reason that I stamped this one, because air is actually homogeneous, but unfiltered air is not. If you've ever looked at air, at sunlight coming in through the window and you see little things floating around in the air, that's what this is talking about. So yes, you can see stuff in there. An apple, well, an apple has skin, it has the stem, it has all those seeds, all those parts, right? So it's definitely granite. If you picture granite, you know that there's lots of different colors in it. That tells you that it's a hetero. Iron with rust. This time we have iron and we have iron with rust. So this is a mixture. In wood, of course, if you picture the wood grain, you can see that there's a different composition that is seen throughout the wood. So that's where you're going with that. All right, so make sure you know what these are. Stamp them or do whatever you need to do on your side so that you'll have them. So now I'm going to clear these and we're going to go to the next part. Okay, so clearing. And I'm going to the next part. The next part is getting a little bit more complicated. Notice we've got 3 things that we need to classify. So first we're going to start with elements. These are easy. They're the ones in the periodic table. So aluminum is 1. Nitrogen, right? Sulfur, mercury, and that's it. There's nothing else. Okay, now compounds we're going to stamp with a star again. All right, so compounds. See, carbon dioxide. That tells you there's carbon and oxygen. Sulfuric acid would be a compound. Water is a compound. Air is not a compound, and no, none of those are. Okay, so solutions is the next one. So we're going to stamp it with heart. Let's do a heart for solution. Okay, so solutions are going to be hearts. Okay, sugar and water. You can see that there's not going to be any sugar left after you stir it really well, right? So that's what you want to do that. Gasoline, you know, gasoline looks the same throughout, even though it is a mixture. Water and instant coffee, air, and grain alcohol. And to do the last one, let me see if I got anything else to stamp with. I've got this one. Okay, so for heterogeneous, we're going to use this guy. Okay, so obviously we're going to talk about this. An orange, once again, we're going to have different types of things in an orange, right? A pencil, you have the wood, you have the lead, you have the eraser. Raisin bread, well, you have the bread and the raisins, just that. If you can see them and you can differentiate between them. And carbon particles are dark and sugar is white. So yes, you can definitely see that difference too. So there you go. So I don't know why this is stamped over here, but I need to erase that one, don't I? Because that one's just out there in the middle of nowhere. Okay, there we go. So there you are. That's how we're going to classify things. Okay. So it helps to know what things look like before you get there, right? And that's one of the things that I was telling you, is that you have to picture him in your mind's eye, and then it'll make more sense. Okay, let me clear all of these and go to the next one. Okay, for the next one right here, we have a visual. Now, in this case, we are going to have five things that we're going to classify. So you got A, B, C, D, and E, right? All right, so if it's an element, it's going to look, if you read the directions, it says each circle represents an atom, and each different color represents a different kind of atom. So if two atoms are touching, then they're bonded together. So if we want just element, no mixture, just element, 5 would be 1, right? So this one you would put A. Let me see. Can't do an A. There. Okay, so that would be A. Nothing else here is, oh, I lied. There's a 7 too. That's also an A, right? All right, and that's all I see that is an element. Remember, A is element, B is compound. Now, it says that 2 bonds, like right here. See, this is a set ratio. You have 2 white ones to 1 black one, and they're all the same. So that right there is a compound. So we're going to say this is B. This one's not. It's a mixture. This one is not. This one's a compound too. Why do we say that? Because we have 2 white ones and 4 black ones in each one, exactly in the same spot. You see that? And that's it. The rest are mixtures. Okay, so C, we have a mixture of elements. The mixture of elements, that's going to be 2, right? That's going to be a C. I said a mixture of elements because you have 2 balls of different color, right? But they're single. You see how they're single? They're not touching each other. So that's going to be a mixture of elements. So is 9. It's hard to tell, but 9 is a diatomic element like oxygen and or whatever else is diatomic, and I will go over those later. But and then a single atom one. So whatever it could be, it's a mixture. All right. Then we have a mixture of compounds. That means nothing but compounds. And this one right here classifies as a mixture of compounds because you have a compound that is 2 black ones in the middle and 4 white ones on the outside. You see how there's 4 of those? And then there's 4 of the other kind. So that is a mixture of compounds. So in this case, that is going to be D, right? And this is not, okay, so that's the only one that classifies as D. And then the last one's E, which we have a mixture of both elements and compounds. So here we have an element, right here, right? We have an element, and here we have a compound. So let's see, let me get a spotlight so you can see. Okay, so right here, come on, spotlight. Here, right here, right? You can see that we have a compound, and this right here is an element because both, even though they're bonded, they're the same. And an element is just atoms of the same kind, right? Doesn't matter if they're bonded or not. So this is an element, that's an element, this is an element, that's an element, and that's an element. So it's this one, right? And this one. All right, so you see how you can tell. Okay, so we're looking at mixture of elements and compounds. So in this case, oops, no, I don't want to annotate. I want, yeah, I do want to annotate, but I want text. Okay, so the last thing we have is E. And this one right here is an E because we have both a compound and an element. Here too, we have 2 elements actually and a compound in this one. You see that? Okay, so we've classified all of the first 9, right? Now we're going to classify the rest of them. Okay, let me clear these. And we're going to go to the next part of it. Right. So now we got from 10, 11, 12, 13, and 14. Okay, so is there an element at all in here? No. So there's no A's left in here. However, we do have B. We have a mixed, well, we have no compound, nothing, just compound. Oh yeah, there it is. Number 11 is just compound. If you look at it, it's just one kind of compound, right? So that's a B. So we are going to put this one as a B. There are no A's left though. Okay, so that's a mixture of, that's no mixture, that's just compounds. The next thing that we need is a mixture of element and compound, and that would be this guy, right? He's a C. The next one we have is a mixture of compounds, and that's this one right here. That's a D. That's a D. And that's a D also. And so is this one, right? They're all D's. So you can see, because this is a mixture of, oops, I'll put C. I meant to not, that's not a C. Sorry, that is an E. That's what I meant to put on there. Yeah, that's a mixture of element and compound. So that's an E. There's no mixture of elements either, right? So there's no C's. There's nothing with just elements left. As you can see, they're all compounds. So we have mixture of elements and compounds, compound, mixture of compounds, mixture of compounds, mixture of compounds, and mixture of compounds. All right, and that's that. That's the end of that one. Okay. So we're going to clear all of these and proceed. Now we have not learned how to do physical and chemical changes yet. So we're going to skip this and go to the next one, which is where we classify some more stuff. So let me get to that. We're going to skip this page and we'll come back to it when we learn that. But we are now classifying. We do one thing at a time or it gets confusing. All right, notice here it says write an E in the blank if it's hetero or O if it's homo. So it's easier for me to stamp it. So I'm just gonna stamp it like I've been doing. Stamps are easy because I don't have to write anything. So we're gonna say if it's hetero, no, if it's homo, oh, darn it. Okay, if it's homo, we're going to stamp like that. Okay, so if it's homogeneous, just think about it. Does it look the same throughout? Yes. Does this look the same throughout? Yes. Salt, it's just salt, right? So yes, it looks the same. Dirt doesn't look the same throughout. No, that one does not belong there. I accidentally stamped it. Air, air definitely looks the same throughout, doesn't it? Air, you know, it's just air, not unfiltered. Milk looks the same throughout, but we're gonna not stamp it because it is a colloid. And there's where, if you look at it under the microscope, you would know it's not the same throughout. All right, so the next thing is hetero. All right, for that one, we're gonna use the other one. All right, so we're gonna stamp it with a heart. No, not a heart, a star for hetero. Okay, so wood, like remember, there's wood grain, so you can see differences. Lucky Charms, you definitely can see differences. Dirt, you can see differences. Such as sausage and mushroom, just that right there told you it's a mixture. And milk, it is a mixture that is heterogeneous. You just would have to see it under the microscope, like I said, to know that. But it is also a colloid, so you have to remember that too. It does not allow the light to shine through it, right? So that's the main thing that you have to remember. Okay, so once again, we're going to stamp these next ones, and we're going to call them element. We're going to do the elements first. And elements are gold. There's nothing here else. Silver, it's an element, and that's about it. There's no other element, right? All right, so the next one's going to be compound. It's going to be the little star. Okay, so water's a compound. Seawater is not. Sugar's a compound. Air is not a compound. Carbon dioxide is a compound, though. Ice is a compound because it's water. It's just frozen. And the next bunch of them are going to be mixtures. So we're going to use that one. We're going to use the heart for those. All right. So for these, seawater, well, it's a mixture of salt and water. So it's a mixture. Chocolate sundae, well, you know what chocolate sundae looks like. Air is a mixture of different gases. And a Big Mac, well, obviously a mixture. Okay, so there you go. So that's mixtures right there. Okay. So we have different kinds of mixtures on here. Okay, the next one, we're going to skip anything with physical or chemical, like I said, because we haven't covered it yet. We're going to go cover it now, and then we're going to come back to it. Let me see if there's anything else. Oops, don't do that. If there's anything else, I'll do that too. That's funny. There was a little heart up there. Yeah, no. Okay, the rest of it we haven't done. So we're going to go back, and we're going to go to our PowerPoint. So we were looking at this PowerPoint, remember? We had finished up to a point. Oh, here we go. Sometimes it takes a little while to open up. Okay, we had looked at all of that, but we didn't go to physical through chemical changes. All right, so we were looking at, come on, where did you go? There we go. All right, so yeah, okay, we talked about, okay, so you have different changes that matter will undergo, and they are physical and chemical. They can either be microscopic, which means you cannot see them, right, with the naked eye, or they can be macroscopic, which you can see with the naked eye. Now, here's some properties of matter, and all of these are physical properties. So electrical conductivity, if are you able to carry electricity? Yes or no, then that's a yes or a no, basically. And there's some degrees of really good conductors, poor conductors, and no conduct, does not conduct electricity. Heat conductivity, same thing. Density, we talked about that one, which is the mass to volume ratio. Melting point, that is the temperature at which something changes state, becomes a liquid. Boiling point, it becomes the same thing, a gas. Index of refraction, that is bending light as it passes through it. Malleability, it can be hammered or beaten. See, that's the index of refraction. That's what we were talking about when we talk about the Tyndall effect, right? Malleability, can it be hammered or beaten into thin sheets like aluminum foil, if you think about it, or gold foil? Ductility, drawing into a thin wire like copper. Copper, you can draw it into a thin wire, and copper is a good conductor. So you have two of those right there, right? Two of its properties right there. All right, so let's go. Okay, so what is a physical change? This is what you have to think about. Oops, sorry. The main key words here to me are right here. It changes state, but does not change. Sorry, does not change chemical composition. See? Okay, so if you're freezing water, right, you're going from water, which is liquid, to ice, which is solid water. If you're boiling water, you're going from water, which is liquid, to gas, which is water vapor. So all of that is water. So you're not changing the composition of the water, you're just changing its state. Like another one, cutting a piece of wood into smaller pieces. The pieces are still wood, you just change the size and the shape maybe. See here, it says the form or appearance changes, right? But the properties are the same. You see that? So that's a physical change, okay? Okay, so let's go to the next one. Let me clear all this little highlights that I did. All right, so for that, remember what a physical change is, because we'll be looking at it. Okay, so here are some physical changes. Melting points, boiling points, vapor pressure, color, state of matter, density, electrical conductivity, solubility. People think solubility is a chemical property, but when you dissolve something, you're not chemically combining it, you are physically combining it. So no, it's a chemical. It's a physical, it's a physical change, not a chemical. Adsorption to a surface, that just means attaching to something. Hardness, that's like diamonds, probably one of the hardest things on earth, right? So that's what it's referring to. A chemical change occurs when a substance changes into something new. See there, see the big difference? It changes into something new. This occurs due to heating, chemical reaction, etc. You can tell a chemical change because the physical properties change. Okay, so all of these are physical properties, but they have changed. And a lot of, remember why we said they can be macroscopic or microscopic, and these are the ones that can be seen, right? These are the macroscopic changes, like you can see bubbles forming. The mass changing, this sounds weird, but basically what it is there's gas being formed, so the mass changes because of that, or it's being used up to make something else, and that's what that means. But mass changed. That's a little bit of a sticky word to put on there, but it's okay. If it's explained, it's okay. All right, so let's go to the next one. Okay, so here is your chemical changes. See, if you look at the words, they always have some sort of action word. Reaction with acids, reaction with bases, reaction with oxygen, ability, see, to act as an oxidant or act as an oxidizing agent, act as a reducing agent, reaction with other elements, decomposition, you see, corrosion. Every single one of these is doing something, right? It's changing. That's what that means. These are all changing. That's why they're action words that you have with any kind of chemical change. Okay, so let's go to the next one. All right, so this is the other thing. This is two words that you need to know. And I like to kind of break them a little bit. Now, extensive. The word extent. The word extent means quantity, right? So I'm going to type here. And intensive means internal. That means inherent. So basically, it doesn't change. So if you think about it, let me do my little. Okay, so in this case, intensive is going to be more like internal, inherent. What else can we call it? And let's call it inherent. So in other words, it is part of it, right? So if you think about these two words, quantity or extent, and I'm going to put that because extent means quantity, right? Right. So if you think about these two words, then it's easy to define these. Okay, let me clear that and go to the next one. So go to the next one. There we go. All right. So intensive properties such as density, color, and boiling point do not depend on the size of the sample of the matter and can be used to identify substances. So here's the key words. Do not depend. So they're inherent, right? They don't depend on anything. They are part of who they are, okay? Whereas extensive properties do depend on the quantity. So remember we talked about extensive, thinking of extent meaning quantity. See, there it is, quantity. They do depend on the quantity. So what does this mean? Well, let's think about it. If we're looking at different types of things, right? Different types of properties, we can kind of tell which one's which by looking at this. Okay. Oh, sorry. So sodium, for example, these we're going to stamp. I'm going to stamp again. The intensive properties, hardness. Will it matter if it's a piece of it or a big chunk of it? No, right? So hardness is going to be intensive. Color. If you have a piece of a material that's red and you cut it into lots of pieces, is the colorless? No. Melting point. If you have a little chunk of ice and a big chunk of ice, is it going to melt at the same point? Yes. So all of these are intensive. You see that? They don't change. Density. Density doesn't change because the more mass you have, the more volume you take up. They're all physical properties, but they all intensive. Every one of these. Okay, let me clear that. And go back on to next one. So these are all physical properties because you don't have to change anything either. Now, chemical properties, they can change or react to form other substances. So then that's the key. If you must react or must do something to change the identity of that substance in order to test the chemical property, then yes, that is a chemical change and it is a chemical property. you see? So chemical properties are not just measured like these are. You can look at them and you can measure them. You see that? Without changing anything. Because density, all you have to do is measure mass and volume and you got density, right? A melting point, all you got to do is put a thermometer in and you know when it melted. Color, well, you can look at it. Hardness, you can measure that too. It's called, what was it called? Oh Lord, I can't remember. It's a scale that you use. Anyway, Mo, it's called Mo, the Mo scale. So, all of these are physical properties. And every one of those was an intensive property to make it interesting about that. But there could have been other properties that were extensive in there. Okay, so chemical properties describe, like I said, how it changes. So in order for you to figure out a chemical property, you actually do have to affect a chemical change. Oh, Lord, what happened there? All right, so one of the chemical properties of alkaline metals, such as sodium and potassium, is that they react with water. In order to determine that, you would have to combine it with water and observe it, you see? And when you combining it, it reacts. See, reacting means it became something else. So, in other words, you have to define chemical properties by the chemical changes that it undergoes. All right, like right here, this is a picture of a lot of chemical and physical properties. I'm not going to read them all to you, but you can look at this thing, which is mercury oxide. Mercury 2 oxide was heated. And upon heating, it goes back to oxygen and mercury. So this is what is known as a decomposition reaction. You notice the mercury right here is these little white particles, and the oxygen's right here in the gas phase. You see that? So it does separate. And look at how the physical properties change. You can just look at it and see that. It went from being golden, kind of like copper color, to being white. And this gas. So yes, you can definitely see the changes. So that was chemical. Okay, so we already did this part. All right, so we looked at physical and chemical changes already, but we're going to do a little bit more. There is I think I want to say this one, but let me make sure this is the one. This PowerPoint is pretty good too. It actually goes through the classification of everything here. But we've already gone through all of this, so I'm not going to, we're going to look at the states of matter another time, so we're going to skip that. Okay, so remember how I was talking about that graphic organizer I had made, and I told you to use a word? See, like right here, they're using their own words, but you don't have to use these words in yours. It says, can it be separated by physical means? The answer is yes. Then you have a mixture. Is it uniform? The answer is yes, you have homogeneous. If it's not, then you have hetero. Can it be separated by physical means? The answer is no, you have a pure substance. Can it be decomposed by chemical means? The answer is yes, you have a compound. No, it's an element. All right, so that's how that one works. And we're not using separation of a mixture either, not yet. Okay. Oh, we're not doing that just yet either. Nope. Okay, so that's it. Like I said, this one just goes over the chemical changes. And this is what's happening here. This is a chemical change. How do we know? Well, what's in here is some sort of gas, and it's being burned. It's being burned. It gives out light and heat, which wasn't there before, right? And you got reactants changing into products. So yes, and we know all of that. Atom, element. Yeah, hold on, compound. Intensive and extensive. So there you go. Depend on the amount of matter present. And here's some examples. Volume, See, extensive volume. Yes, the more stuff you have, the more volume it takes. So yes, it does matter how much. The more you have, the more mass and energy content. Think of calories. If you eat a piece of cake versus the whole cake, you have a lot more calories with the whole cake, right? So that's what you have to think of. Does it have more if I have more of it? And the answer is yes. Here, melting point, no, it doesn't matter. It's inherent. Okay, so physical changes, here we go. A change in any substance that does not involve a change in the identity of the substance. For like right here, for example, you burn boiling water. See, that's not going to change. And those are phase changes. And we're not going to talk about those just yet. Nope, 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 not yet. All right, so we're just talking about what we know. Okay, so based on that, we're going to go back to the matter packet and we're going to go and see if things are physical or chemical. Remember that sheet I said we were coming back to? We are going back right now. Okay, so if it's physical, let me see, I'm going to make it bigger. Okay, so if it's physical, we're going to add a stamp. Okay, so salt dissolving in water is physical, right? We're just going to put a check, yes or no, you know, whether it's physical or chemical. All right, hydrochloric acid reacts with magnesium to produce hydrogen gas. Is that a physical or a chemical change? And you can just put it in the chat as P or C as I talk, and that makes us have a, let's see, sorry, I'm trying to find the chat. There we go. I'm going to open it so we'll see it. Okay, so go ahead and answer. Is it P or C? Oops, sorry, I gotta undo that one. Just put it on the chat. No, nobody? Can you notice it says reacts? That's the word that we were looking for. Remember, it's an action word. So it is a chemical change. Okay, what about the next one? Piece of copper cut in half, P or C. You know what? Instead of, do you know how to do the pen reactions? Let me see. Where they're on the bottom of your screen and you can do a thumbs up or, where are you? I can't find mine, but I know they're here. I just can't find them right now. I was gonna tell you can do that if you can't find the chat, but the chat's down below on your screen on the very bottom. If you put your mouse on it, it should say chat, and it has like a little bubble, like a talk bubble. It's better if you actually do participate, and I don't want verbal because verbal tells me what it tells me. It gives the other people the answer. That's what I mean. So I want to just have you send it to me like this. See how I just did it to everybody? Okay, so that's all I want is for you to just put it on there. Okay, since I already gave you the answer, I'm gonna go ahead and put it on here. What about, is a sugar cube ground up? When a sugar cube is ground up, is that a physical or a chemical change? I'm looking for your answers on the chat. Come on, everybody. It's very good. Okay, anybody else? Okay, only one person answered. And
hi, Miss Bides.
yes.
Because I'm in mute.
You
I
can't
didn't
find
I didn't see
it. You can't find it.
it.
Okay, try to look for the chat, because that way it's quiet, you know, and not everybody knows your answer right away.
Yes, ma'am.
Although if you send it just to me, that would be better. That way I get the answer and nobody else sees. So
Okay.
where it says to everyone, you can just change it to one person. So like I'm sending it to you, Cece. See, I just sent you that one and nobody else can see that.
Yeah.
Right, Henrietta?
Oh, Miss
Only
Venus.
you could see it, right, Henrietta?
Yeah. Miss Venus.
Yeah. Yes, ma'am.
Who's that one? Jacqueline just texted me. She said she's in the
Mm-hmm.
Asasla RN, something like that.
Mm-hmm.
And she said she gonna be online later. I don't
Okay,
know. Yeah.
gotcha. All right.
Thank you.
Mm-hmm. Anyway, so do the P or C. All right.
Okay.
So,
Peace. The whole thing.
mm-hmm. Yeah, we're gonna do
Okay.
P or C on the chat. Just put P or C on the chat.
Okay.
So the sugar cube is ground up. You have to think about it. If I grind up a sugar cube, do I still have sugar? If the answer is yes, then it's a physical. If the answer is no, then it's a chemical, right? So in this case, the answer is yes, we still have sugar. Okay, if we heat water to steam, is that a
Mm.
physical or a chemical? Which one is it? Come on, you. Okay, so is that a physical or a chemical? Hmm? Okay, water's still water, right? So the answer is physical. Iron rusting. Okay, now see, here's another word, another action word. Iron's no longer iron, it's rust, right? There you go. Ethyl alcohol evaporates. Is it physical or chemical? Evaporation is a change of state. So obviously, yes, it is physical. Okay. Ice melting, another change of state, right? So once again, physical. Milk souring. Okay, now think about it. Does the milk that you know still look like the milk that you now have? Right? No, something changed. The smell changes, the taste changes. That means that's no longer milk. So that is going to be a chemical change. Sugar dissolving in water. Okay, do you still have sugar and do you still have water? Yes, you do, because you can recover them, right? Sodium and potassium react. See, there's the word, react violently with water. Is that a chemical or a physical? That's going to be a chemical, right? Because,
Coming right now.
okay, pancakes cooking on a griddle. Okay, if you think about it, when you're looking at
Uh,
pancakes cooking, you see liquidy stuff. It becomes a little more solid. That could just be a change in state, right? But what about the little bubbles that form on top? Were those bubbles there before? No, that means something new is being produced, and that would be a chemical change. Grass growing on a lawn. Okay, this one's a little tricky because if you think about it, it is changing size, and size is physical. But what does it take for it to change size? It takes a chemical reaction known as photosynthesis, right? So you can actually see a change in length, but it doesn't come from just anywhere. So it is a chemical change. If you put air in a tire, you're just changing the amount of air in it, right? So that's a physical. If you're digesting food in the stomach, okay, once again, the food does not come out looking like it did when it went in. And a lot of it is used up. So that means that was a chemical change. And water being absorbed by a paper towel, can't you just squeeze the paper towel and push that water back out? Yes. And you can also dry it and evaporates. So yes. So you see, you've got chemical and you got physical, and it's kind of easy to tell which one's which if you just think about what I'm telling you. All right, let me clear these because we have a few more. And unfortunately, if I lift it up, these are not going to be in the right spot. Okay, so we have mounts. Okay, there we go. Oh, there weren't that many, but okay. So we said water absorbed by a paper towel was physical. Come on. We said that was physical and this one was chemical. Okay. So alcohol boiling at 79 Celsius. It's still alcohol. Alcohol is just changing state. Paper burning, on the other hand, you no longer have paper, you have charcoal. See how you changed? Water freezing at 0 Celsius. That's a physical. You still have water, you have ice. Fireworks exploding, obviously a chemical change, right? You have light, you have noise, you have things that weren't there before, smoke, smell. Alka-Seltzer giving off carbon dioxide when added to water. Well, if you think about it, when you plop those Alka-Seltzers, they were tablets in the water was just water. Now you have fizzy stuff and it's dissolving. And it's dissolving because of a chemical change. And clouds forming in the sky, all it is condensation, right? So condensation is a physical change. And there you go. That's the whole entire thing. So that is how we know a chemical from a physical change. It is a thing that you have to think about. Is it changing the composition? What is it doing? Oops, sorry. Do that one because that one's confusing there. All right, so let me get clear of these and let's go on to the next one. We already did these, so we are going to skip those, but we do have these. Now we have a P or a C. Once again, I'm not going to write P or C because it's harder for me, so I'm just going to stamp. Physical is going to be a check, and we're going to think, okay, colors are physical, right? Density, remember that was physical. Burns, easily we're going to skip. Boils, definitely physical. Reacts, no. Conductor, see, it conduces electricity or heat. That doesn't change it. Dissolves in water, that's solubility. Melts, that's just the physical. And malleable, that means you can make it into thin sheets. So, but it's still aluminum if you did aluminum. So the chemical ones obviously are the ones that are left, right? But we're going to talk about it. Burns easily. In order for you to figure out if it burns, you actually have to burn it, right? And burning changes things. Not affected by acid. It says not affected, but doesn't mean you didn't add acid to it. So you did do a chemical property. Reacts violently. Oh, that means you know that it's going to change. And that's it. The rest are all chemical. I mean, physical. So that's only 3 chemical properties on here. Obviously, chemical properties are more common, right? And then here we have physical or chemical changes. Same thing. We're going to do the stamp. We're going to do a check for the physical ones. Okay, so grinding chalk into powder is still the same thing. Dissolving salt in water, you still have salt and water. Tearing a piece of paper, you still have paper. Stretching copper into wire, you still have copper. Hammering gold into foil, you still have gold. Melting ice, you still have water. And making hydrogen. See, all of the rest of them, you can kind of see how they are now being changed. So we're going to go with the stars. Dissolving zinc in acid. Well, it's dissolving, but it's also producing a gas as it dissolves. So therefore, it is a chemical change. Burning gasoline. Well, can you put old gasoline back in your tank? No. So you have a chemical change, right? Digest food. Well, food doesn't look the same and you cannot bring it back up and look the same. So no, it's a chemical change. And if you are making hydrogen from water, water is a compound. That means you have to pull off the hydrogen from it by a chemical change. You see that? All right, so here we're going to do intensive and extensive. And for those, we are going to do, once again, the stamping. We're going to intensive, it's going to be check. So let's see, mass. So intensive, that means it doesn't matter how much of it you have. You do have more if you have more mass, so no. Density doesn't matter because the more mass you have, the more volume you also have. And density is a ratio, right? Melting point never changes. Color doesn't change. Oops. Well, you know, I meant to put it there. In length, no. So the rest must be extensive because if you think about mass, if you have more mass, it weighs more, right? If you have more volume, it takes up more space. If you have more length, it's longer, see? So all of these matter on the amount that you have. So you must have more of whatever it is in order to have these properties. Okay, they increase or decrease. All right, so that's that one. Let's clear that one. And let's go to the next page. And let's see what we got here. Okay, we have the periodic table. We've done pretty much all of this. So now the next thing we're going to do is we're going to talk about the changes in state. And that's where that PowerPoint was. So we're going to skip this. We'll go back to our. Okay, so right here, we're going to go to changes in state. Okay. Okay, here we go. And this is a physical change. So that's what we're talking about, changes in state. Okay, so state is a way that matter presents itself. So you notice it says it is a change that doesn't involve a change in the identity. So all changes of state, like phase changes, which is what we're going to look at. All right, so we're going to look at solid, liquid, gas, and plasma. Okay, so we have these four states of matter: solid, liquid, gas, and plasma. What are the differences? You notice it says you're adding heat. So you add heat to change a solid. Just think of ice, right? Just think of ice. If you take a piece of ice, you add heat to it, right? It becomes a liquid. You add more heat to it, it becomes a gas. It will never become plasma though. But the more heat you have, plasma becomes ionized particles. And that's what this is. This is a charged gas, basically, is what you could say. All right, so solid, a solid. If you think of a solid, anything that is solid has a definite volume and a definite shape. The particles are packed in fixed positions. So basically they retain their shape, right? Anything that's solid retains its shape. Liquid, you have a definite volume because you can measure a liquid in a container. but it also takes up the shape of that container, which means it doesn't have a definite shape. And their particles are still close together, but they're no longer in fixed positions. And a gas has neither one of the two. It doesn't have a definite volume, nor does it have a definite shape. They are at great distances from each other. Now, particles, the one thing that you have to remember also is gases can be compressed. So you can put a lot of oxygen into a tank, for example, right? Or you can let it go and it just fills up the room immediately. So, you know, it does expand and it does compress. So either one. A liquid cannot be compressed, not really. And if you put pressure, enough pressure on it, becomes a solid. So, because you're forcing those particles together again. So it's a gas. You can compress a gas into a liquid if you keep pushing more. Okay, so plasma is a temperature, very high temperature gas that has particles that are charged, which are called ions. Like the sun is made of pure plasma. Okay, so here we have the three phases that we were talking about. Plasma is actually the most common state of matter in our universe, but not on Earth. Okay, so we have particles in a solid. See how they're close together, touching each other. They're fixed. Particles in a liquid, they're very close together, but they're no longer keeping shape. And particles in a gas, they're all over the place. Okay, so here's copper as a solid. You see that? Look at the temperature. The temperature, it stays solid all the way to there. And now we're going to go liquid. Liquid is separating a little bit more, right? And look at the temperature. I mean, it's a liquid at this temperatures. That's high temperatures. That's because this is a metal. And the gas, it's gonna take a lot more energy. But you can see the differences between them, right? Okay. So, yeah, that's it for those. Okay, so let's look at one more diagram that I have on here. And this is phase changes. Well, let's do the kinetic molecular theory first. I made this diagram because it helps you understand the changes that have to happen in order for something to change state. Okay, so look, over here we have all the words we need. Okay, so in order for you to go from a solid to a liquid, that word is called melting, right? From a liquid to a gas, that word is called evaporation. From a gas to a liquid is called condensation. From a liquid to a solid, sorry, it's called freezing. Now there are two other words that you may not have ever heard, but you've seen them happen. Because if you've ever seen dry ice, it's called sublimation. It changes directly from a solid to a gas. You notice it doesn't skip through liquid at all. So dry ice sublimes. It's called sublimation, okay? And gas to a solid is called deposition. Something that you've never known probably, but you've observed, frost, right? And all it is frost. It gets so cold that the gas, the water vapor in the air falls as solid immediately. So that is known as a deposition. It does not go through a liquid, then a solid. Okay, that's what frost is, a deposition. All right, so these are your words. Now, I've also drawn some arrows on top so that you understand that you're going from the lowest over here as a solid to the highest over here as a gas. okay, of these three things. Temperature, if you think about it, ice is cold, right? So the temperature is low. Water, room temperature, right? If you're just, and then you've got, if you're gonna heat it some more, then you're gonna become a gas. So that's gonna be hot because water vapor burns. Okay, so you see how the temperature is increasing from left to right on this diagram? Kinetic energy. All kinetic energy is the measure. If you measure the kinetic energy of a system, you're actually measuring its temperature. So that's all temperature is. That's why when I asked you to do temperature and heat, I wanted to know the difference between temperature and heat. Now, temperature is actually the average kinetic energy of either one of these things. So the average kinetic energy of this one is much lower than the one here, which is much lower than the one here, right? So that means that the highest kinetic energy is going to be found in the gas, which is, if you think about it, kinetic energy is energy of movement. Gas has a lot more freedom to move around, therefore its temperature is higher. Makes sense. Whereas over here, it's like you're packed sardines, right? And you can't move. Therefore, your kinetic energy is going to be low. See how it matches with the temperature? And then the distance. If you don't have much distance to move, you can't move very much. Therefore, your kinetic energy is low, so is your temperature. Same thing with liquids. Same thing. You've got a little bit more room. Your distance is a little bit bigger. Your kinetic energy increases a little bit, and your temperature does too. And with a gas, you have gotten biggest distance between them. So that means you move the most, which means your temperature is the highest. Now, the last thing is looking at what is known as intermolecular forces. All intermolecular forces is attraction between the molecules of something. So in this case, the molecules of water attract each other because it is a polar substance, but we'll look at that later. But if this is water, and also there's other.
Alida! Alida!
I'm muting him. Okay, so, and those, and these right here, right? We are going to go the opposite, because if you are closer together, aren't your forces more likely to be attracting you, right? They are likely to be attracting you. So the intermolecular forces are going to be higher in a solid. And then the liquid is in between. And then there are no intermolecular forces virtually present in a gas because there's no attraction between molecules because they're so far away, right? So it makes sense. So just think of this diagram when you're trying to explain, the intermolecular forces, not intermolecular forces, sorry, the kinetic molecular theory of a gas also, but of matter. So basically, the tighter packed they are, the more intermolecular forces they have, the less they move, the less kinetic energy, and the less distance, right? So all of that works together, and so on and so forth. Okay, so that's how we're doing that one. Now, let's look at phase changes. So what are we looking at here? Okay, here we are looking at, and I'm gonna make it a little bit bigger so you can see it better. Okay, here we are looking at changes. Let's say this was ice and we're boiling it. We're heating it. So you have a point in which it plateaus. That right there is known as the melting point of water. The melting point has a measure of something called the heat of fusion. In this case, for this amount of water that was here was 80 kilocalories per gram, okay? So 80 calories per gram. That's not very much. And then you're gonna heat it some more. You notice it's gonna be ice and water over here. It's gonna change and it's gonna once again now be water and steam. Here it was water and ice, right? Here's just water. Here's water and steam, and here's just steam. So solid, solid and liquid, liquid, solid, liquid and gas, and just gas. You see how that works? Okay, so this right here, you notice how much longer it took to break up all those intermolecular forces. That is known as the heat of vaporization. And it took 540 calories versus 80 to get all those molecules from from a solid to a liquid. It took 80 calories per gram of ice. Whereas here, it took 540 calories per gram. So that's a lot more energy, right? And the intermolecular forces are present. Here, they're very, very strong right here in these places. The intermolecular forces are very strong. Here, they're weakening. Here, they're gone. You see? So that's what you have to remember. All right, and here you've got boiling point and melting point. And these are the two important numbers. And over here, if you look at this is heat. Remember, heat is a transfer of energy. So here we're transferring energy from the molecules that aren't in the high enough energy to go as a liquid. So we're transferring the energy from this liquid here to the solid, and that's why this remains a constant until all of the molecules have changed state. Then it goes up and keeps going, and then it hits another plateau between liquid and gas. And right here, this is where all of that heat is taking place, that heat exchange. But it is even because you have the molecules here that are lower and the molecules here that are higher, and these are helping these come up here and fix and go away. So, that's how it works. So remember, heat is a transfer of energy. So that's what's going on there. Okay, now let's go to the next one. And we're going to look at one more diagram, which is pretty much like this one. But in this case, is a phase changes chart. And if you look at it, this one is looking at time and temperature. Okay, so the time, solid to liquid to gas. So you're adding heat here, you're removing heat here if you're going the opposite way. So every time the plateau hits, you either have the melting point if you're going towards gas, right? Or towards liquid, or if you're going away from solid to liquid to a solid, you got the freezing point. But they're the same. Melting and freezing point are the same. It's just which direction you're coming from. And boiling and condensation point are the same also. It's just which direction you're coming from. It's just when you hit that temperature. In this case, if you want to do it in Celsius, the boiling point is 100. So if you hit that 100-degree mark, then you are at the boiling point. Here you hit the 0-degree mark and you're at the melting point or freezing point, either one. You see? Okay, so that's all that is. Let's see what else we got. All right, so the next thing that we would be doing is looking at how to separate mixtures based on what we were talking about. All right, so let me go to this one first before we go there. Oh, come on. It's thinking about it. There it goes. I hadn't opened it yet. I was like, wait, I'm probably gonna have two of them now. No? Okay. So right here, we have kind of like a review of what we just talked about. So let's look at it. Okay, so you have the flow chart. The
Is Ali
surface,
absent?
I'm muting in. The matter, right? Can it be physically separated? The answer is yes. You have a mixture. If it's no, you have a pure substance. Then your mixture, can it be, is it uniform? The answer is yes. You have homogeneous, right? And if it's no, you have heterogeneous. And you notice here, they just, since there's only one, they just put solution, but actually not all homogeneous mixtures are solutions. So, well, mixtures, yes, but they're known as solutions, yes. And heterogeneous, you have colloids and suspensions. And then you have, can it be chemically decomposed? The answer is yes, you have compound. If there's no, then you have an element. Now, let's take it one more. If you say here heterogeneous, you say, does it settle? The answer is no, it's a colloid. If the answer is yes, it's a suspension. And here, does it exhibit the Tyndall effect? The answer is no, you have a homogeneous mixture. And if the answer is yes, and they're talking about if it's a liquid or a gas, the answer is yes, then you have heterogeneous, okay? So, all right, and here's some examples of elements. Graphite, which is what's in your pencil, is pure carbon, and that is an element. Pepper, if you look at it, is a heterogeneous mixture because you can see the black and white specks on it. Sugar, that's a pure compound. All of it looks the same. It's very homogeneous looking. And there is a formula to sucrose, which means it is in constant composition. Paint, if you think about it, you have to take it to the counter, they shake it, that means it settles. That means it's heterogeneous mixture, and to take it one step further, it is a suspension. Soda is, if you look at soda, when you pour it out of the, when you first, before you open it, all that gas is in it, and it looks all the same throughout. And that is when it is a, you can tell that it's a solution because it looks the same throughout, so it's homogeneous. All right, let's keep going. All right, now we have elements. And here is what I was talking about. Copper. See, all of this, even though it's a wire, right? It's all copper, nothing but atoms of copper. So this is an element. There's nothing but copper in here. In aluminum foil, there's nothing but atoms of aluminum foil. Aluminum, sorry, aluminum foil. In the aluminum foil, there's nothing but atoms of aluminum. So that's an element, nothing but one type of atom. Here you have a compound. You have compound which is composed of two or more elements in a fixed ratio. The properties differ from those of individual elements. If I told you that salt by itself, if you took sodium by itself, every time sodium is exposed to air and air has water in it, has water vapor, or to water directly, sodium will ignite. It will burn quickly because it's very violent reaction to it. So can you imagine if every time we ate salt, we had a burning in our stomach? That would not be cool. So yes, obviously the properties change, right? And then chlorine is a gas. And if you inhale chlorine, you die. So think about it. Separate, they will kill you, both of them. But together, you put it on your French fries, and you can eat it. So yes, definitely a change in properties right there. And then you remember that they have to have the law of definite composition, which means that you always have the same ratio. For example, let's think of some compounds. You have water is H2O. See how we know that the composition of water is H2O? We have carbon dioxide is CO2. We have, methane, which is a gas, CH4. See, so They're all fixed. Same amount of hydrogen atoms, same amount of oxygen atoms. If we add one more oxygen atom, remember I told you that was not going to be water, that's going to be hydrogen peroxide. So if you change the composition, if you take one of these carbons, one of these oxygens off, now it's carbon monoxide, so it just changes. Now, the other thing is elements can combine in different ratios, and here it's proven right here, see, in these two, right? See? So you have both. You have always the same for each compound, but then they can combine in different ratios themselves. So these are the two laws that all compounds behave by. Law of definite composition and law of multiple proportions. All right, so let's go to next. Okay, so here's one example. Two different compounds, each has a definite composition. And they both contain the same elements, but in a different ratio. So there's the multiple. Now here you have a variable combination of two or more substances. And that is, it can either be heterogeneous, which is like granite right here, or homogeneous, like this apple juice. You notice they put the apple behind it so you didn't think it was beer, because it looks like beer too. Okay, so heterogeneous here is a non-uniform composition. So in other words, it doesn't look the same throughout, like salad dressing, like Italian dressing. If you look at it, the oil always separates, right? So you have to shake it. So that's a suspension. Examples are sand. Sand, if you look at sand, it doesn't look the same. Granite, vegetable soup, etc. Homogeneous, though, has a uniform composition. Examples are salt water, bronze, sugar water, air. Solutions. This is what I was telling you. It does not exhibit the Tyndall effect. They do not settle. For example, rubbing alcohol right here. That is 75% alcohol. So if it's 75% alcohol, that means the other 25% is water, right? So that means it's a mixture. But you can't tell where the water is and where the alcohol ends. All right, a colloid though, this is milk. That is heterogeneous. It is medium-sized particle. It does exhibit the Tyndall effect and they don't settle. And the next one is suspension. So you have heterogeneous again. Large particles. Tyndall effect is exhibited. The particles do settle, like example, lemonade. I mean, lemonade, you gotta stir or your little particles of lemon go away, right? They go down to the bottom. So that's why. Maybe not the juice itself, but the particles of the lemon will go down. So you've got this. Okay, so here's some examples of colloids, suspensions, and solutions. So you've got mayonnaise is a colloid, because when you make mayonnaise, what you're doing is you're trapping fat into the protein and making an emulsion. And it doesn't settle, right? You don't have to stir mayonnaise. Muddy water, on the other hand, settles out, and that makes it a suspension. Fog doesn't settle. Fog is a colloid. Salt water is a solution. Italian salad dressing, just by the fact that you have to shake it, you know it's a suspension and also a mixture. All right, so that's how we know. All right, now in order for you to separate things, you have to know their properties. And this is where we're going to look at some separations. There are some techniques, and they are not all mentioned on here, but the ones that are mentioned on here are important. So make sure you pay attention to these. All right, so we have, all right, so whenever you look at this, you know that a pure substance, it only has one type of particle. and a mixture contains more than one type of particle. Okay, so a liquid can be either pure or it can be a mixture, right? Because water can be water. If it's distilled water, there's nothing in it. Or tap water, which has our chlorine, fluorine, all this other stuff that people add to it to make it pure. Purer, no, but drinkable. It's not pure. It's a mixture then. All right, so in this case, it's asking you which of these is a mixture. Based on your definition, mineral water, minerals added to the water, that's right, it's a mixture, right? Orange juice, you know that juice is going to have vitamins, it's going to have sugar, so obviously that is another mixture. And coffee or tea, that's another mixture. So all of these are mixtures because they all contain more than one type of thing in them, right? Okay.
Mhm.
So when you have a solid and a liquid, you have a mixture. Now, this is your thinking if you have a solid and liquid added together. If you say, does it dissolve? The answer is yes. Then this is what you'll see. You will no longer see the solid. The liquid may or may not change color. Think of Kool-Aid. Okay, so that's why it says may or may not change color. And a solid that dissolves in water is soluble. So that's another word that you need to know, soluble. And if the answer is no, then this is what you'll see. You will still see the solid. Like think of putting sand in water. You can stir it all day long, but that sand is not going to go anywhere, right? All right, so you will still see the solid. You will see the liquid, but there will be no color change because there's no mixing. And a solid that does not dissolve in water is known as insoluble. So these are two words that you needed to learn. Okay, so here's some more words that you need to learn. Okay, so when you have a solution, you have a solid that's dissolving in the liquid, right? And it forms a special type of mixture. Okay, so if this beaker, we're going to make a solution in it. This right here, which is the water, is known as the solvent. Okay. So solvent is the liquid that does the dissolving. Okay. That's what is known as your solvent. It's always, not always, but yeah, always more of that than of the solute, which is the other word. Solute is the substance being dissolved in the solution. So let's say that was sugar and water or salt and water. The water would be the solvent, the salt would be the solute. And when you put them together, you get what is known as a solution. Once you stir it, there's nothing left. Then you've mixed them. But can you separate them? Yes, you can, because all you did was mix. You don't have a chemical reaction. You notice there's nothing that changed except the color. And the reason they did a color change is just so that you would see that there's a solution forming. The only reason they did a color change is because whatever solute they added to it had a color to it. And that's when it changes, like Kool-Aid, for example. All right. So in order to separate things, you have to think of two things. Okay, so you have to think about this. How would you separate pasta from cooking water? And you can talk if you want. How would you separate? What do you normally do when you cook pasta?
Boil the water, boil the water
No.
first.
I mean, after separate, when it's cooked, when you want to just the pasta, what do?
Drain
Drain it. How do you drain it? What do you use?
it with the colander.
Colander. That's right.
Oh, yeah.
That's right. That's what I wanted you to say. What about how do you keep tea leaves out of tea?
dissolve the tea bag in the hot
The tea
water.
bag, that's right. That's right. It's a tea bag, right? So they're contained in something. And how do you do coffee from a coffee pot?
Put the paper thing.
Yeah, a coffee filter. Guess
Yeah, the
what? This is
filter.
called, this technique is called filtration. And everything that you're doing here, you're filtering. And why are you filtering it? How are you filtering it? Because of their size. See, the
Mm.
pasta is larger than the holes in your colander, right? The tea
Yep.
leaves are larger than the holes in the bag that's keeping them inside the tea bag.
Mhm.
The coffee grains are larger than the filter that you put to keep the coffee from going into the liquid part. All right. So see, this is all known as filtration. And all of these are insoluble solids. That's the other thing. The pasta is never going to dissolve in water. I mean, it might get mushy and ugly looking, but it's not going to dissolve. The tea leaves are not going to dissolve either, and the coffee is not. So insoluble, remember the word insolubility? Okay, so insoluble solids can be separated from a liquid by filtration. Okay, remember that. Okay, well, we're just going to skip this. This is a bunch of baloney. Okay, okay, so the sea is a very big mixture. And yes, in the sea, you have solids such as fish and boats and people. But the
Mhm.
salt part is the hard part to separate. How would you separate it? Well,
The water, the seawater.
yes, how would you separate the
Oh,
salt from a salty seawater solution?
uh, dry it. Get the water from the sea. I saw
Right,
it doon in the,
right. Yeah, there
and
you
then
go. No,
dry it,
you're
and
right.
it became
You're
salt.
correct. That is known as evaporation. So you do
Yeah.
evaporation. See? So you're going to remove the liquid from a solution. It is called evaporation.
Yeah.
So all the water will be gone
Mhm.
and you will be left with the solute, right? So the solvent you're evaporating and you're catching the solute. All right. See, that's before evaporation.
Yeah.
That's after evaporation. All right. So,
Oh, okay.
all right. And we're just gonna skip this too. Okay, the solution mining though is kind of neat. So basically, this is how they get rock salt. Um,
Mm.
this is how they harvest it. They take it, which is known as solution mining. So what they do is they take water, pump it into the
Uh-huh.
rock salt layer. That forms what is known as brine, which is salty water. They pump the brine out, right? And then they dry and purify, they filter it and all that good stuff.
Oh.
And then is dried, like I said, and you get the salt.
Mhm.
Isn't that cool?
Yeah.
So, see, it is what we just talked about being used in a real life situation. Okay, chromatography. This is kind of how DNA, and I'm not going to say this is DNA, no, but this is kind of how DNA works. When they do DNA analysis, kind of, okay, kind of. I'm not saying this is even close, but it is the same principle as far as the size of things. Okay, so when you are doing this, what is known as chromatography, what you do is you take these little pencils and you mark, or you put a little line of, not pencils. This could be water soluble markers. You can do this at home with coffee filter right here. And you can put a dot of black, a dot of red, and a dot of
Oh.
yellow, and you will see them separate into different colors. Um, what you do is you do not want to touch the water to the dot that you put, right? Because if the water touches, it's going to dissolve into the water. So that's not what you want. What you want is you want the water rising up the filter, because the filter absorbs that water. And as it absorbs the water, it's going to touch those two. And since it has a medium that is carrying it, right, it's going to pull them up and slowly leave them behind as it keeps rising due to their size. So obviously the yellow is a lighter, it's a heavier compound than the red. You see that? But the red is above. So if there was something below that, that would be even heavier than the yellow, but there's nothing below. And black would separate into several colors actually. And that is what is known as chromatography. And what you're doing is you're separating things that are soluble in the same solvent, but very small amounts of it. Okay. Okay. So how do you separate the solvent? So if you want to keep the liquid part, not the solid part, right? Then what you need to do is known as distillation. And it involves 3 stages: boiling, condensing, and collecting. And this right here is known as this part, this tube area. This is known as a Liebig condenser. Right here, this guy. Okay. And that one is the most important part because that's where all of it happens. Well, except for the boiling part. The boiling part is right here. But the other 3 parts happen here. You actually are cooling the stuff with the water that's coming in here. You're cooling the gas that's going through because, you know, gases rise and they will expand. So they will go into, they'll be forced into this tube. The tube is now cooling down the gas and it becomes a liquid, and then it drips down through gravity and you can catch it. And this is the collection phase. So here's your boiling phase, right? Your condensing phase and your collection phase. Okay. Okay.
Don't go to Alida. Alida, come here.
And the reason you want the water to
Alida.
come in the bottom and
Where?
go out the top is because the water is hottest
Never put anything
here,
on your hair.
right?
Do you
The stuff
understand?
is hottest
Never.
here.
It's a chemical. It will ruin
So
your
you
hair.
want this to be replaced constantly.
You understand that?
Whereas if
listen to
you
me.
had done it the opposite, then the water would be replaced here and that wouldn't matter.
Put it on you, not her.
Okay.
You won't listen anyway.
Anyway, so we have that next part. Let's see what else we got. Okay. All right. So now here goes. This is the choices that you have when you have a solution. We have, is the solid soluble or insoluble? Well, if it's insoluble, then you know you separate it through filtration. But what if it's soluble and you want to collect the solid or the liquid? Then that's another 2 techniques. So this is how it works. Okay, so if you want to collect the solid, remember, that was evaporation. If you want to collect the liquid, that was distillation. Okay, so let's look at a matching of what we learned today. All right, so we have some descriptions. How would we match these? Okay, so evaporation, is it A, B, C, or D?
Alida, come here. Come here.
A, B, C, or D?
Okay, evaporation.
Evaporation is which one? A, B, C, or D?
Don't ruin your hair with the chemical. She won't listen. I mean, you can hear me. Okay.
Okay, let's read. Remember what evaporation was. We are separating a soluble solid from the liquid, but we want to obtain the solid, right? There's the key, the solute, right? So that means that's a match, right? Filtration, this is insoluble. So insoluble right there. See? Because like pasta and tea, remember that? Okay. Then we got chromatography. Remember I said small amounts that are soluble in the same solvent. So that is chromatography. And the last one, of course, is distillation, but let's look at it. Solvent, we are obtaining the solvent. See, you notice the words B and C are exactly the same except for the last word, right? And so that's what matters. Distillation is going to be the solvent. You see that? So there you go. That's how you measure. All right. And now let's go back. And I bet you will be able to answer the questions that we had. Come on, escape this. Oh, it's not letting me escape. It does that sometimes. It says, no, I don't want you to leave. Come on. It's not letting me escape. There we go. Finally. I had to click it so many times, you know. Okay, so we're gonna close that one. All right, so let's go back to our packet. And we're going to answer those last two questions that we hadn't answered. Okay, I use text. And I'm going to make it a little bigger so you can read it. It's not letting me. It's not letting me do it. Hold on. Cancel. Why are you not letting me make you bigger? Oh, I know why. That's why, because I had it already. Okay. All right, so how do you separate sugar and water? Okay, remember, we need to right? See? Or in this case, water, right? In this case. Okay, how would you separate alcohol and water? Well, since you want the alcohol, you want to do distillation, right? Okay. And how would you separate sand and water? Well, here's where we think, is sand soluble or not? Remember, it wasn't. So then you can filter the sand that is the solutes. So, oh, insoluble, sorry, I should say insoluble solid. Right? Remember that? Water, which is the solvent. Okay. Does that make sense? So those are your three. Pretty easy now, right? Now that you know the properties, it makes it easier to separate them. Because now we are going to have a question in our test that is a, hold on, let me go back to, I need mouse. There we go. Okay, so we're just going to clear it out. Told you it stays. Okay, so you notice here you have a rubric for essay question. And here's your essay question. Okay, so when you open this, you're gonna have a little chart. And this chart is just there to help you figure out what properties you're gonna use, how you're gonna separate it, blah, 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 right? So obviously I'm not gonna go over how to do it, but I am gonna go over a different one. This one you're gonna use, yourself, but that's what's in the thing. Okay, so let me go and show you how I would do this. Let me go get my one that I use. Okay, that's the lab. Stop it. Let's see if this is the one I want. Yeah. Okay. So this was a lab, right? And you had to separate these things. We have sand, salt, iron filings, poppy seeds, coriander seeds, and all of that. So obviously you would want to mixture. You would want to know the mass of the whole thing first, the mass of the container, the mass of each component. So this is where you're going to start going, figuring out which ones to do. So the very first thing, and this is the only part you're going to do, is to make the plan. Okay, that's the first thing we're going to do. It's just the plan. All right, so we're not doing the whole lab, right? But we have these things to separate. So we remember sand, salt, iron filings, poppy seeds, and coriander seeds, okay? So let me go get, let me do these. Okay, and I'm going to use a different sheet completely, a brand new one. So I'm going to make one just like what you had. Insert table. Let's see, I need it. Four steps, 5 things. I think that was it. I want to say. So the component goes here, right? Okay, so here I'm going to paste those. Okay. All right. So the very first thing that we need to figure out, and remember that other thing was you want to know, let's see. I'm just going to copy this one that we had before. See how it's got material or component. Okay, so we need one more. It's 5. It's 1, 2, 3, 4, 5, 6. 6 of them. Okay, I'm gonna add 6, and then I'm gonna paste it. Okay, so we only have 4, so I need to add 2 more columns. Doesn't matter which way. Just need to add 1 more. Okay, so now I'm going to paste those up here that I just copied. Ooh, no. Just the one. There we go. All right. So we had the same thing except different, right? All right. So the order of separation, that's important because you don't want to do it in the wrong order because you're not going to end up separating them. So you have to think, okay, so poppy seeds, I don't know if you've ever eaten a poppy seed muffin, but they're basically about that big, right? Whereas coriander seeds are probably by that big, right? Maybe a little bit bigger. Okay, so you can already see a difference, right? All right. And they told you what you had to use on the other one. So I'm going to bring that over too. Oh, let me go back to mouse. Okay. This is what they told you you have to use. Beakers, magnets, fishnets, sieves. So I'm going to bring all this equipment back over to our little thing that we're writing. So I'm going to put it up here. Okay, down here. It won't let me put it up there anymore. Okay, so this is what we have available to do the whole separation. Okay, so we know iron is magnetic. So I would take this guy and I would use the magnet, right? That would be my number one step. Oh, I said Control V, sorry. I didn't Control C it. I forgot about that. I highlighted it, but I didn't copy it. There we go. See, I'm using the magnet. That would be our order of separation would be 1. And I'm only doing this as a plan. Remember, we're planning it right now. All right, how we separate it, okay. Then you describe here, pass the magnet over the mixture, which, okay. Okay, and the property would be magnetism, right? And there are no additional steps, like not here. Okay, so that's your first one. Now, we have sand, salt, poppy seeds, and coriander seeds. The most and the properties that we know about sand is that it's insoluble in water, right? Salt is soluble. We know that poppy seeds are going to be insoluble. And we know that coriander seeds are also going to be insoluble. Okay, so we have a lot of insoluble things. We can't use that. Okay, so we know that much. We do know, though, that sand, if you put it in water, is going to sink, isn't it? So we know that density is important here. Oh, density. Oh, Lord, I cannot type today. Density. All right. And we know poppy seeds are very small, so they're probably going to float. So we know density here too. All right. Coriander seeds are larger. You see that? And we have sieves with 1 millimeter hole. 1 millimeter is definitely less than that. So we're going to use filtration right here. Okay, so filter, let's see, sorry. That would be how to separate. Yeah, you are going to filter the coriander seeds out by passing them, the mixture through the sieve. Okay, and so we know we're going to use this as a material right here. So that's number 2. So look at what we have left. Oh, and this is also size, right? This is size. This is the one thing we're definitely going to use is size. Because the size was so much bigger, right? That the poppy seeds are going to stay behind, but the coriander seeds are going to stay. So that's our second step. There are no additional steps here. Right now, however, in order for what we know about insolubility, solubility, and density to take place, we are definitely need to add water. So our next step is actually, yes, there is a step here, add water now. So that really would be step 3, right? That would be add water. Now, once we add the water, what's going to happen, if you think about it, you're going to have sand that's going to go down. So you're going to have a beaker. Draw. Okay. So you're going to have a beaker, right? You're going to add your water. Your sand's going to be right here, right? Your salt's going to dissolve throughout, and your poppy seeds are going to be up here floating, right? Up there. So you're going to now, yeah, there we go. I just want to put them right up here, but you can't see them if I don't put them in a different color. Let's say these are your poppy seeds right here, right? They're going to all be right there, up there, floating around. Okay. Your sand, let me erase this part. There we go. Your sand is basically going to be down here, right? And when you just leave it red, that's fine. And then you have all of your salt that's going to dissolve. So look at what we have left. We have to read and see what are our choices. Oops. No, sorry. I lost it. I meant to come bigger. There we go. What are our choices? Okay, so we use the sieves, we use the magnets. Okay, so the next thing that we have small fish nets. I think we can use these to catch the floating poppy seeds. So we're going to put that right there. Boom. Okay, so how will we separate it? We're going to filter out, right? Oops, the floating poppy seeds. Using the fish nets. Okay. All right. So obviously we needed a beaker in here somewhere when we added water, so we needed a beaker too. So beaker goes in all of these pretty much because they're in a beaker. All right, so this is step 3. We have retrieved those now. Now all we have is sand. So all of these are now gone. So let's erase these. Boom, they're gone, right? Oops, I didn't mean to erase the whole thing, but I can redo it. Okay, so we have this left, right? And we also have a little bit of sand, right? We have that. And so now we have the sand down here and we have the salt water. Right, so we know the salt water is soluble and the sand is insoluble. So we're still filtering, right? We're still filtering because the sand is now at the bottom. So we need to stir it a little bit and use a filter again. So once again, but this time we have a different kind of filter. We have the coffee filter, you see that? So we're gonna copy that one and we're gonna stick it on there, coffee filter. And we're gonna use that for the sand. Okay, and in this case, we also have size because remember, size is what? The insolubility, the density, and the size. All of these are helping us separate this one. So how are we going to separate it? We're going to stir the sand into solution for a little bit because this is going to be and pass through the coffee filter. Or I can't type. All right, so now all you have left in this beaker right? All you have left in the beaker is one thing, and that is your salt water. And you notice I'm still leaving it red up there, but this shouldn't be red. This should be black now. Okay, so this is all we have left, right? Is this one thing. Yeah. So, but in order for you to pass it from one to the other, you're going to need to catch. See, so we had to move this onto another beaker. That's why I'm making a different color beaker. And we're going to make it not white. Let's make it blue. Well, let's make it yellow because it's not exactly perfect. Okay, so we're using a separate beaker that we put the sand. Okay, and so we need to add a little bit more on here, right? We're still not finished. So we did do that. Make sure to collect the salt water in a beaker. Okay. Right, so that's so that people know that you got to still catch that other stuff in a beaker. So there we go. Okay, so now we have salt and water, right? So what do we do? Well, remember we have also hot plates. Hot plates are to heat things, right? So we're going to use those. And we just said we're using a beaker, right? So we have a beaker in there. And we also need a watch glass. The reason we use a watch glass for this is if we don't put a watch glass on top of this beaker, oops, I meant to put it yellow so it looks more like glass, but hold on. Let me undo that because I meant to draw it. There we go. It's a watch glass, right? So it looks like that. Then as the hot plate is heating this, right? Then this keeps the salt. It still lets the steam escape through the sides right here, right? But it keeps the salt that's going to be popping up and down from going anywhere. Okay, so that's what the watch glass is used for. All right, so we need hot plate, watch glass, and let's see. One thing we needed was a beaker too in the sand one, because we do have a beaker in it. It is in a beaker, so we're using a beaker too. It's already in the beaker. All right, so in this one is heat the salt water to evaporate the water from the salt and separate from the salt. Oh Lord, I can't. Told you I can't type. Okay, there we go. All right, so we use solubility, but we also use boiling point, right? Because we're boiling it. And we also use, what else? That's it. That's all we really used. All right, and there you go. So that's how you would separate it. Now, the thing tells you to write a step by step. So that's why we did this, so that we could actually write a step by step. So let's clear the drawings. And now you would be writing a step by step. So this is, you want this to be a procedure that people can follow, right? So step one, you could say spread the mixture. See, I cannot type today. It's just terrible. I'm thinking ahead and pass the magnet to it. To retrieve the iron filings due to magnetic. Okay, See, you just used everything that you wrote on one. Oh, I forgot to put. This is 4 and this is 5, right? So that's the order. See how you're writing every one of those in here? See, because that helped you come up with your plan, but now you need to actually write the plan, right? Number 2. Okay, notice it says coriander seeds. Okay. Pass the remaining mixture through, that was good, the sieve to remove, to retain the coriander seeds. Coriander. Okay, there we go. Due to their size. See? Boom. We just did all of that. We said what we're doing, what to use, you see that? And why, right? 3, add water to the remaining mixture. In a beaker. So now you know everything else is in a beaker. That's step 3. So you're going to have one more step than you have here because yes, there was another step. So number 4, which is really 3. Okay, you say filter out the floating. See, okay, you can actually just copy that. I'm not going to even, it's already there. There we go. Using the fishnets due to size, floating poppy seeds, and you can put here lower density. Using the fishness due to size, period. And insolubility. No, you know what? Due to size, period. You can put here the insoluble floating poppy seeds, right? Because that's what it's going to be. That way I know that you used all of your stuff. And then the next one, 5, would be the sand. Okay, so you can just write down, see, just redo this, Control C it again, put it down here. Okay, now you need to put on here due to their size, right? The insoluble sand. And then higher density here, you could put that. That's why it sank, right? We know that. Okay. All right. And then last one is 6, and let's see. Put the beaker containing salt water on the hot plate and cover with much glass. Period. Heat the mixture so that the water evaporates fully and leaving only salt behind. Okay. And you could put here boiling point. Boiling. Okay. The salt water And that you could put salt dissolves in water, right? See, so you're saying here that it was soluble. There you go. See, we just did it. And now if you were on a lab, right, and you wanted to do this experiment, you could just read these steps and know exactly what to do, right? You see that? And then somebody could have used the tweezers. I mean, there's other options here, but the tweezers to remove somebody said, could we use the tweezers to remove the coriander seed? Yes, you can. It takes a lot longer, but yes, you can. You know, in my case, I would use the sieves because they got small holes, and neither the sand, the salt, or the poppy seeds are going to get caught in there, only the coriander. So that's why. Okay, so that's how you would do your essay. That's how it's going to look. Okay, and you're going to make sure you do all three. And if you look at the rubric, which I'm going to go get right now. Hold on, let me go get that rubric. Let me go back and get that rubric, so I can show you how I'm going to evaluate this. Okay, so there it is. It's 30 points. So you need to do this. Okay, so there's our rubric. All right, so I'm going to make this rubric smaller so we can use it back and forth. Okay, so look over here. It says, we're only reading the bottom part. Oops, darn it. I meant to put it so that I can see only the bottom part. Hold on. Let me get this down more. There. And get that little rubric up again. There we go. Now we can see only the bottom part. Okay, so the very first thing that we're looking for is, did the person separate the things? So obviously these are different things. So, you know, if this was the rubric for this one, it would have those components on it, right? So the sugar, were the correct properties identified? The answer is yes. Okay, so you get those 2 points. Were the correct materials used? The answer is yes, so you get those points. Was it a valid description? Yes. Was it incorrect? Obviously, no. So you got those 4 points for your sugar or your sand or your salt or whatever it is, right? And same here, same there. So you can get up to 4 points each. And then, did you write the step-by-step procedure? See how I wrote the step-by-step? That's 10 points of your whole thing. So are all steps included and defined? Yes. Left out 1 or 2 steps, 8 points. Left out 3 or more steps, 6 points. Did not write, 0 points. So if you don't write it, if all you give me is this, you're going to get only 20 points possible. And that doesn't mean you're going to get all 20 points, because some of this might be wrong too. You know, so what you gotta do is you gotta go look online, and you can see some of these things are already pretty obvious, but you can look online and see what are the properties of, let's say you don't know properties of nickel, for example. What are the properties of nickel? Physical properties, and it'll tell you. And so when you look at them, one of those properties is going to go ding, 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 and you're going to know how to do it. Okay. And same thing with the 5mm. That should be 5 centimeter. I noticed there's a typo in there. Okay. I need to change that. Yeah. So 0.5 centimeter grass beads and 1mm holes. Yeah. Otherwise they would go through too. All right, so that should be, I'm going to correct that right now while I'm thinking about it, because there is a mess. There's a question on here. I'm going to correct it in both. supposed to be 0.5 centimeter, not millimeter. Where are you? Oh, there we go. I'm gonna, no, I don't need that. Actually, I do need to edit the settings. Because I need to download that, change it, and then upload it. No, I need to enable editing too. Okay. Okay, there we go. All right, now save it. So it's 2. Let's make it summer. This is spring. I'm gonna make it summer. I don't usually change them. I change up, like for fall, it'll be a totally different question. But for right now, this is what it's going to be. Okay. All right. So we're just going to close this off. And this one, I should say 0.5 centimeters. And then I'm going to file save that too. I'm going to call it summer. That way I know which one it is, right? All right. Boom. All right. So we're going to delete this one. Yes, because I need to correct it. It was wrong. Choose file. Quick access. And say summer. Oh. There we go. Upload it. All right. So that one's that one. That one's done. And I'm going to do the other one here in a minute. One more. It takes it a little while when it saves it. It goes right back to it. Okay. So now we're going to the question for the essay test. You also need to edit it. You know, this is due July 31st. And there is this. See, I'm going to delete it and put a different one. Yes. All right, there we go. So now it's corrected. Okay, and that's that. It was a typo, and I carried the typo over because I didn't finish reading it. But yeah, there you go. That's your essay question. And pretty much we're done with this. So now the one thing we didn't do and we're going to do, and I would like to do that in person, is the periodic table one. Although, I mean, we could do it now, but it's over anyway. So we're going to do that next time. So the last part of that packet, which I'm going to give you in person myself, right? It's doing that periodic table activity and then looking at metals, non-metals, metalloids, and the different types of compounds. And that's it, ladies. We are done for this day, and I will see you next time. If you have any questions, I'm here for you to ask me. So I'm going to go ahead and stop the recording.